Okay, so we're going to talk about multi-threaded programming and what the difference between processes and threads are, process states and state transitions, and then once we start multi-threaded programming, we're going to, there'll be the possibility of having some hazards, so we have to figure out a way to solve these hazards. Okay, so what is a process? Okay, I think this is from Wikipedia. So in computing, a process is an instance of a computer program that is executed. It contains the program code and the current activity. So you write a program, you put it on your hard drive, and then if you decide to run it, the operating system will create a process and start running your program. Okay. And there's a couple of
exe files are processes.
Well, no, so this is saying that is a program, and then if you ran it, it becomes a process if it's running live on your operating system. So the exe file that you create from compiling in C or C++ creates a program. And then if you say its name, or the name of the output file, it will start running, and that's a process running on your operating system. And so, for example, then the bottom here is saying that opening up several instances of the same program means that you have more than one process being executed. Okay. So process, this is like a kind of a crash course in operating systems, but when your operating system lets your program start running, your program can bounce around from state to state. So it goes through the created process, that's when you first enter the command, type the command in to run the program and hit enter. The operating system will go through a process of creating the process for you. And I'll go through a little bit further what the operating system is doing on behalf of your program, but then your program gets put into a queue because you're on a multitasking system. There's other programs running on your computer at the same time, and they can't all run at once, so they'll all take turns in running. So for example, if you have a computer running and you have a web browser up and you also have, you're logged into school here and you're running a program, you might have 2 or 3 programs running at once, but you only have one processor on your computer. So how does it do that? Well, it lets each program run on the processor for a fraction of time, and then it saves its state, and then goes to the next one, and keeps doing that. So you'll be created, and then you'll probably be put in a queue waiting to get on the processor. Then you move over to the processor. Now what if as you're running you ask for a resource, like you want to use the printer, and it's not available because someone else is currently printing? Well, then you'll get the operating system will make you wait until you're done printing, and then you'll be able to go back to running again. Or you could go from waiting for something, then go, I'm sorry, you're blocked from executing because some resource you're looking for is not available. Then it becomes available, you start using it, then you go back to waiting, and then when it's your turn, you run again. So you could go bouncing around this cycle for a while. Then also just an operating systems concept won't really matter for multi-threaded programming, but you could be asking, the operating system could allow pages of storage into memory to run your process, and if you haven't been running for a while, the operating system might take those away and write them out to disk. If they get written out to disk, you might get called a state called swapped out. So again, this is if you, in your operating systems class, they'll go into more details on this. So basically you're bouncing around from state to state and eventually you terminate. So that's for a process. So now a question goes like this. Suppose you were writing, so that was just a very, very brief slide on something you'd cover in an operating systems class. But now suppose we had a question, this is back to a programming class. Suppose we had a question like this. You're writing software to run a clock. You have a method or a function called add 1 second. That will add 1 second to the current time of day. So the body of this code in our example here would be like take the number of seconds, add 1 to it, and then if seconds equals 60, we would set it back to 0 and then add 1 to the number of minutes. Then if minutes equaled 60, we would set it back to 1. No, if minutes was greater than 59, we'd set it to 0. And then add 1 to the hours, and if hours was greater than 12, or if it's a 24-hour clock. So this routine would basically say whatever time it is, add 1 second to it, and handle minutes, hours, and so on. And then we also had a method that allows us to set the time of day, because when you have a clock, you'd like to, from time to time, change the time of day. Maybe there's daylight savings, or maybe the power went out and the power came back on, and you need to set the time from time to time. So suppose you wanted to be able to run the add 1 second in a loop forever. Every second it adds 1 second to the time of day, so it's running the clock. But you'd also like to occasionally run the set time method. So how can you write a program that can do both? How could you do this, is the question. So we could do something like this. We could say while one, meaning an infinite loop, add 1 second, and then let's say there was some operating system routine that says go to sleep for a second, and then it comes back and adds another second. So this would just run over and over and over, and it would keep the time of day. Okay, and then later on we say set the time to 3:20 p.m. Okay, any comment about this? Well, I haven't. This routine will never run because the clock is just constantly running. So then, is there any other suggestion we could come up with? Suppose we set the time and then started running the clock. So basically what I'm doing here is I'm sequentially doing the 2 steps I want to do. And if you think about it, there's a lot of other operations we'd like to do on a clock besides set the time. We'd like to set the alarm.
Play the radio.
Yeah, play the radio. A lot of once in a while functions we'd like to call. Plus this one needs to run constantly. So is there?
Access the router.
What's that? So let's say we had something that needed to run constantly, but then on occasion do something else. How could we do this? Pretty much wherever we put this code, once this starts running, we can't do anything else. Right? So does anyone have a solution?
Use multi-threaded program.
Yeah.
Ask the compiler.
So the idea is basically this. We have kind of two tasks that really can't be done sequentially. For whatever reason, they kind of have to be done. This one needs to run for a little while, then maybe that one can run, and if nobody wants to set the time, we can come back to this one, but we have to somehow keep going back and forth. Okay, so now, back to the operating system. How does an operating system manage processes that are in its system? And then, like we said before, once in a while a process could be blocked from doing something. So, I hope these pictures come out in the video. But anyway, the operating system maintains, most operating systems, Windows and Linux, maintain a pointer to what they call the ready queue. The ready queue points at this is not your process, not your exe file, but this is a control block that has data about your exe file. What's the most recent step it went to, what are the values of the registers at any point in time. And this ends up being a linked list, and it's actually a circular linked list, that basically says this process is the one, let's say, that is currently running, and then this one will run next, and then this one will run next, and then when this one's done, we'll go back and run this one. And this will keep going until these things finish, which means they'll be deleted off of the queue. So then, as these are running, and they each get a fraction of a second, and so on, and you could start doing things like saying one's high priority, one's low priority, so they get more time. That's an operating system design issue. But let's say one of these processes asks for something that's not available at the moment. Let's say this process asks to go to the disk drive, but the disk drive is busy servicing some other process at the moment. Would you want to leave this process on this queue and just say, all right, I'll go to the next one since the disk drive is not ready. This will run for a little while, come back to this one. This runs for a little while, now we're back to here and this thing says I'm still waiting for the disk drive. Do you want to use up part of the processor to keep saying, I still can't proceed, the disk drive is not ready? Or would there be something the operating system can do to not waste the processor's time if there's a process like this one that is waiting for a resource that's not available at the moment? It may become available in 20 minutes, but you want to keep spending time saying, I can't proceed without this resource. So what the operating system will do is it just plays around with this data structure. It basically says, if this thing is making a request for a resource that doesn't exist, then I'll just make the pointer of the A process, its next pointer will point to C, and then we'll take the B process and put it on the end of whatever the queue is it's waiting for. Let's say the disk drive has process D is queued up for it, and now B comes in and also needs the disk drive after D is done. we'll just put the block of B on the end of this queue. We actually don't even have to move the blocks. All we have to do is have this point to point here, and this point to point here. It's just changing 2 pointers, and now all of a sudden B is waiting for a disk drive, and A and C are the only ones that are considered ready. So now, A runs for a little while, C runs for a little while, A runs for a little while, C runs for a little while. We never waste time with B, because B is stuck waiting for something that doesn't exist. Okay, so this is basically one of the tools an operating system will use to manage these processes. And so what's good now is we can make, the computer can look like 3 programs are running at once when actually only 1 is running. They're just time slicing the processor. Then the question becomes, suppose you get moved down to one of these queues for something that will not let you process. How do we eventually go back to the ready queue so we can process again? Something will have to, like the disk drive will have to move us back there. Something along those lines has to end up happening. Now what we could do in multi-threaded programming, this is basically the same picture, but we can decide to allow our process to say I would like my process to split into 2 mini processes. So it's the same exact concept as the operating system, which is handling multiple processes. Now I'm saying my particular program is going to split into 2 sub-processes, which we'll call threads. And then I'm going to say, okay, I want one thread. When the operating system comes around and says, I'm allowed to have some time to run, I'm going to have kind of my mini operating system within my program that says, I'm going to let this function run for a little while, then I'm going to let this function run for a little while, then this one, and then eventually that's time out, and it goes to B. But when the operating system says, I'm allowed to run, I can split my program into 2 or more threads and let them each take a fraction of the time, bounce back and forth, and then it goes to B, and then to C, and then back to A, which makes it bounce back and forth between thread 1 and thread 2. And everything else stays the same. If the process gets moved to one of these queues, it gets moved in its entirety. Okay, so then there's some things you could just read up. I don't have to read. Well, all right. So threads are not processes. They're a little bit different. They're basically subtasks of a process. A process can grab a resource, but threads do not grab resources on a thread basis. They grab resources on a process basis. So if one of your threads grabs a resource, that means your whole process is grabbed it. And they're quicker to start up and quicker to end than a process because they're subparts of an already existing process. Okay. So what we could do is something like this to solve the question about the let me see. So the question about the run, we could have our run, what we could end up doing is this: we create a method or function, depending on what programming language you're using. If you're using C++, you create a function, and Java, you create a method. We create a method called runClockThread. We give it a name like runClockThread. Basically, forever, it will add 1 second to the clock, and then it will stall for a second. And then it'll add 1 second to the clock, and do this over and over. We have a separate thread that says set the clock. And what this will do is it will constantly ask the person, do you want to set the clock? And if you don't answer it, if you don't say, yes, set the hours to this and the minutes to that, it just won't set the clock. All the set the clock will do is just write to the hours and minutes. If you hit enter, if you say hours of this, minutes of this, and hit enter, it'll set it. Otherwise, if you don't hit enter, it just stays with the old time. And what we'd like to do is make these 2 programs run sharing the processor when our program runs. So then we would say something like, again, this is pseudocode. This isn't C++ or Java or C# code. I'm just going to say start the run clock thread, start the set clock thread. So normally you might think, well, this is a method that we have to wait for it to finish before we can go to the next one. Right? That's the way normal programming. You call a function, you sit there and wait until it's done, and then you go to the next one. But with this new thread idea is that this code, which is the parent process, can say start a thread and it will kick off a child process. That'll run for a little while, but will immediately go back, the parent keeps running. So this thing runs but only gets a fraction of the time of the parent process. So the next thing it does is it kicks off a second thread, and then after that it has nothing else to do. So the only thing running are the two children threads. The parent is done and is not part of the time slicing. Okay? Okay, so this is, I know I'm kind of going through this idea quickly, but all we really wanted to do before was we wanted to take the two tasks that could not run sequentially and somehow come up with a way to make them run parallel to each other. One can run for a little while, then the other one can run, then go back to the first one. They could keep going back and forth. So, yeah?
In C++ and Java, is there like a multi-thread object that you would call?
So,
Declare that you want to use this feature.
it's so, in C++, after the language was created, they added a header file where you can create objects of type threads and then assign when you create the object of type thread, one of the parameters you give it to is a pointer to the function you're going to run. So what we'll do in C++ is we will create a function, not with a name, but we'll say star run clock thread. So that's saying here's a function, and I'm declaring it as a pointer. You can point to where it is. Then when you create a thread, you point to what it is you want to run on that separate thread. And then you call a routine, I think it's called create_thread. But like I say, the syntax is just language specific. When Java came around, they decided to let every object in the world can be its own thread. And then you can code it, you would create a run routine, and then if you call the start method, it will cause the run. You have a method called run, R-U-N, it's a special method name. Anything you put in run for an object will run on a separate thread if you call it by saying start. So, well, I mean, we could go over examples in both languages, but that's what you end up doing. So Java kind of knew this was coming and they baked it into the language, whereas in C++ it was a header file that was added later on. But in both cases, we're doing the same exact thing. We're basically saying I have this function or method, and this function or method, and I would like them to time share with each other. There's other reasons we could do time sharing too. Like let's say you had, it doesn't have to be just two separate tasks that one wouldn't be able to finish. One couldn't start unless the other one finished. Suppose you had 4 independent tasks, but one of them may get stalled. Like suppose one of your tasks was to open up a file, but somebody else is currently looking at that file, so you might have to wait an hour for the file to become available. But let's say you have 3 other tasks that you don't need that file for, you can let those start. You don't have to wait, you don't have to line them up sequentially and then the first thing you get stuck on, everything else has to wait. So you could also do it for time-saving reasons. If you have a program that has many independent tasks, it might be better to put them on separate threads. In case one got stuck, the other ones can go. So there's other reasons besides an example like this one. Okay, so in this case, what we're basically saying is the parent is kicking off children threads, which are basically saying, run independent of me, just time share with me. And so this is an advantage. This, this solves some problems that we have. But now that we have children threads running with each other, it introduces a new problem. And the answer, we'll look at an example like this. So hopefully this gets across a simple point, then you realize this can happen a lot. So suppose we had a multi-threaded programming where program where one thread adds 5% interest to your checking and savings account, and another thread transfers $100 from savings to checking. So suppose you logged into an ATM and you wanted to move $100 over to checking, because you just wrote some check. But the bank also wants to come through and give you 5% interest on all your accounts. That's a much higher rate than banks are now giving, but.
Is it like 1% now?
Yeah. Yeah. And they kind of do it instantaneously, not like in one process, but anyway, suppose this was the case. If you started off with $100 in each account, what would your final balances be after the 2 threads are done? Well, I guess it would matter which thread ran first, right? The one that moved $100 over or the one that gave you interest? So if the one that moved $100 over to checking, if that ran first, you'd have $200 in checking, and then you'd get 5% interest, which would be $210, right? You'd have 0 in savings, 210 in checking. If the thread that gave the interest came through first, you'd get $5 interest in both accounts, and then you'd move $100 over. So you'd have $5 in savings and $205 in checking. Is there any scenario where you'd have 0 in savings and $205 in checking? Or are all of these possible? So, suppose we had the two threads, the transfer thread and the interest thread, and let's say time is going this way. So the transfer thread, which basically has 2 steps to it, it subtracts $100 from your savings account and adds $100 to your checking account. Those are the 2 steps it does. Actually, it should check that you have at least $100 in your savings account before it subtracts it, but you get the idea. We have 2 main steps. Subtract $100 from savings and add $100 to checking. The interest thread says whatever your savings account is, add 5%, whatever your checking account is, add 5%. But suppose this thread ran, subtracted $100 from savings, and then it was said, the operating system said, okay, time's up, we'll get back to you later. And then this thread started running. So like I say, time's going this way, and we don't, when we're kicking off children threads, we don't control when they stop and start. We're at the mercy of the operating system. They can just stop and start us at any time. So we lose $100 from savings, we haven't gotten it added to our checking, and then the interest thread comes through and gives us no interest on savings because there's no money there anymore. We get $5 because we only have 100 in checking. And then we come back and we put the money in. And that's how we end. It's possible. It's kind of a lightning strike situation, but it's possible that we could have 0 in savings and 205 in checking if it happened to follow that schedule that I just showed. And like I say, it's kind of rare. You'd have to be stopped at exactly between those 2 lines. So it's rare but possible. Not super rare. It's not like 1 out of a million. If your program has 10 lines in it and there's 2 lines, if you stop right between those, you'd have bad results. It'd be 1 out of 10 chance it could happen. So it's something we have to watch out for. And so a solution to this problem is an idea of what ended up being called a semaphore. And a semaphore basically means a signal. I don't know if anyone was in the military or...
Yeah.
So did they use the word semaphore to mean signals?
You could use both, yeah.
Okay.
Semaphore, signal,
Okay,
yeah.
so yeah, it was popular in the military. And so back in, I guess, in the 1960s, famous guy by the name of Dijkstra, famous Dutch computer scientist, came up with the idea of how we can get around this problem. And the idea is, so this is again a definition I think off of Wikipedia. In computer science, a semaphore is a variable or abstract data type that provides a simple but useful abstraction of controlling access by multiple processes to a common resource in a parallel programming environment. So the way this concept works is this. The operating system provides 2 functions, and I kind of just wrote out the code, but I kind of just wrote out it in English. The idea works like this. How do we make sure that we don't get into the situation like we had before, where one thread is operating on the checking and savings account, but in the middle of operating on it, the operating system switches over to another process or thread, which then starts altering the values, and then we come back to the first one, and then we have inconsistent data at the end. We lost the 5%, the $5 worth of interest. Is there a way to make sure that doesn't happen? So the operating system will provide 2 what we'll call atomic operations. An atomic operation means once the method starts, this is going to be a function. Once the method starts, if the operating system at any point says, okay, your time's up, the operating system will allow this method, because it's special, it's a system method. It's not one you wrote, it's the one the operating system provides us that we call. It will allow it to run to the end before kicking you off the processor. So now, here's one thing. First of all, couldn't we solve the original problem by allowing you to be able to say at the beginning of your program, from here, from this point to this point, don't ever kick me off the processor? We could have solved the problem that way, right? So this is something good to just bring up. If I was able to put some marker here that says from this point to this point, if I ever time out, let me get to this point, then there'd be no issue, right? Because once I've altered this thing, I must alter this without anybody else doing anything else. That's where the issue comes from. So if I could put in my code a marker that says, once I start here, don't ever take me off the processor, even if I run out of time, until I get to here. That would solve the problem. So why is that solution not used? In other words, why don't programming languages allow you to put some keyword, like don't interrupt me, and then down here, then say, okay, now you can interrupt me. You could not allow that.
You could do that in the beginning and then only put the thing at the end of the code so you can run your whole program without being
So
interrupted.
you know there's programmers who are just going to say, don't ever interrupt my program. It's very important, right? And it can run for hours, and then everybody else is hosed, right? So that would have solved the problem, but we don't have that because it allows the programmer to decide how big the gap is.
Too much potential for corruption.
Yeah. Then people have 3-hour programs and just say, from the beginning to the end, don't ever interrupt me.
I'd love to put that in a video game.
So,
A computer game.
so what the operating system provides is very short programs. These are going to, these end up being about 6 or 7 lines of code. And part of this I wrote in English, but basically if you call this method, this has that special property that if I time out in the middle of it, I get to at least run to the end, and then I get kicked off the processor. And then this is a separate atomic operation. So here's what ends up happening. If you want to grab a resource, for example, the 2 account balances, checking and savings, we're going to create what's called a semaphore. So the semaphore is going to be like a Boolean variable. Either it's available or it's not available. And before you go to use it, you call this P function. And what this function will basically do is say, is the resource available? If so, I want to take it. If not, meaning somebody else has it, then I'll wait. That's the idea of what we want to have happen. We don't want to get started if somebody else is in the middle of operating on these variables. So what do? So the value in this case, let's say if the value is 1, that means the thing is available. This kind of represents the thing we're trying to get access to. If the value is 1, then set it to 0, and I'll take it, I'll proceed. By setting it to 0 means the guy right behind me who also wants it is going to have to wait. If the value is equal to 0, then what ends up happening is the operating system will do this thing. If this thread has the resource, and then this one wants it, and it's not available, this box will be put on the end of a queue for that resource. So it won't be able to proceed. It's no longer on the running queue. So it will not proceed until somehow it gets magically moved back and starts running again. So, like I said, there's a little crash course in operating systems to understand what threads are doing. So when you call this P method, and this, okay, so I'll explain what P and V mean in a second. When you call this P method, it basically is saying, is the resource I'm sharing with other threads available? If so, I'll take it. And I want to block everyone behind me until I declare I'm done with it. The V method is basically what you say, I'm declaring I'm done with it. So you say, if there's anybody waiting for it, then put them back, move them back to the ready queue. Otherwise, just set it back to 1, meaning it now becomes a free-for-all for whoever comes next. So, if there was, we'll just go back to this picture. If there was a process, let's say for example in this case, process B ran and issued one of those V commands for the disk drive. What that would do is say, if somebody's waiting for it, if somebody's queued up waiting for it, then have the operating system move D back onto this queue, so it can just pick up where it left off. And because it now has access to the disk drive. And if nobody's waiting for it, if there was nothing here, well then just set the value back for 1, meaning whoever comes next gets it. So that's what these functions are for. So the operating system provides these two functions, and they actually operate on the operating system. It plays with those pointers to the block, the process control box, to figure out who can go next. The reason why in most of the documentation these are called P and V, has anyone seen these letters before, P and V? Okay, do you know why it's called P and V?
I don't remember.
The guy Dijkstra, who invented it, he's Dutch. And what language do they speak? Dutch.
Dutch.
That's okay. All right. In that language, the word for decrement begins with P, and the word for increment begins with V. And that's why these are called the P and V. Was that?
Pretty cool.
So yeah. But that's really what it's. So it's hard for us to remember.
Yeah, official languages.
So you can just do like
Damn Dutch
IVV.
What's that?
programmers. Official language of the Netherlands.
Netherlands is Dutch.
So should
Okay.
you do IVV every time instead?
IV
IVV, like increment I twice.
or V plus plus. All right. So anyway. So now with these two new functions that have been provided by the operating system for us to use, we couldn't hog up the whole system, but we could do something like this. This would now be the way we would create our threads. Instead of having these two lines, we create a semaphore called X. These two threads agree that the checking account and the savings account together are referred to as X. And before you operate on the checking or savings account, you must get X before you can start. So you do a P, meaning I'm saying, is X, which is the checking and savings account fields, are they available? And if so, I would like them. If not, make me wait. Take me off the ready queue and move me to some place where I'm stuck and I can't proceed. Then, so after I run this line, one of two things is going to happen. X is going to go from 1 to 0 and I can proceed, or it was already 0, which means I get stuck right here. One of those two is going to happen. Once I become unstuck, I can then proceed. And then by doing this, I let the guy behind me get unstuck. And then the transfer thread also does a P and a V around it. So it can't get into this section of code, which operating systems textbooks refer to as the critical section. The section of the code that will cause damage if two different processes are in that same section of code time sharing together. There's a potential for inconsistent data to come out. Okay, so if this thing started running and halfway through this method, which is only a few lines long, it timed out, it will guarantee to get to the end of this method. And then a decision will be made whether this can go forward or get stuck. So now if we tried to do this, if we had the same exact timing situation as before, here's what would end up happening. Let's say the transfer thread went first. It does a P of X, which is really a decrement, the signal variable X. So let's say X started off with a value of 1. That means the first of these two threads to issue the P of X will get the resource and be able to proceed, and the second one would get stuck. So the first one, the transfer thread, gets X to go from the value of 1, meaning the thing's available, to the value of 0, meaning it's now locked, and it can proceed. And it says, okay, savings equals savings minus 100. And then all of a sudden this thread times out. Now the interest thread starts running, and here's where we had the problem before. It could start changing the interest before we do this line. But what it does first is it issues the function P of X. Now at this point X has been set to 0 by this one. So this P of X does what? So the parameter is S here, the first letter of semaphore. If X equals 1, set it to 0 and we're done. But it's not equal to 1, so we have to do the else. Move this process or thread onto the end of the S queue. So now, when we created a semaphore, not only do we have a Boolean variable that sets 0 or 1, we also created a queue in the operating system to slide threads onto, to hold them temporarily. So when this line ran, the X semaphore was not available, therefore the operating system put this thread onto a queue which was created when we actually created the X semaphore. We created a queue, and the operating system put the interest thread onto that queue. So it can't even run anymore. So at this point it can't even run because it's not even on the ready queue anymore. Then this one ends up getting back on the processor because there's really nothing else to run. This line runs, and then this V of X, which says what? This V of X says, when you run a V of X, it basically says if the queue is not empty, then move whatever on the head of the queue back, move that block back to ready. So it'll just start running automatically. And if nobody's waiting for it, then just set it back to 1 so it becomes a free-for-all going forward. So after this line is run, after this P of X is run, the operating system internals looks like this. So here's our program, process A. We decided to split it into 2 threads. We created a semaphore called X, which not only gave us a Boolean to say, a value that's either 1 or 0, it also gave us a queue. This is a pointer to a queue. We'll refer to it as the X queue. When process A ran and got the resource X, it kept running. Then process B ran, which caused the operating system to take this off of the ready queue. So before, this was 2 threads running, sharing the processor, and put us on the X queue. So right now, if the operating system let B run for a while, then C, then got back to A, when A starts running, the only thread that will run is A. I'm sorry, thread 1 of A. It's the only one that will run. This isn't even in a position to run because it's stuck waiting for something. What it's waiting for is to get back onto the ready queue, and what it ends up waiting for is
Yeah, slash.
We'll never know.
so eventually, when this thread ran the V command, it got put back onto the ready queue. And then this was able to start running again. So the way the operating systems, you can cause yourself to stall by issuing this this function. If the variable X is set to 0, meaning somebody else beat you to it. If somebody else beats you to it and then you ask for it, you'll get moved off of the ready queue onto a queue waiting for whoever has it to give it back. If that process never gives it back, what happens to you?
You're stuck waiting.
You're stuck forever. So we can actually, now we've introduced a new problem called deadlocks, where let's say one thread says we can now create multiple semaphores, X and Y, let's say. One process can ask for X by doing P of X, then it could time out. Then another process does a P of Y, gets that resource, then does a P of X, asking for X, and it's not available. You go back to the first one, it asks for Y, which is now not available, and they're both stuck forever. So every time we come up with a new solution, we introduce a new set of problems. So the idea of, and I could go over all the other things that can go wrong. We could also talk about another class. Yeah, how to create deadlocks, and we can set the operating system to find them and break us out of them if we wanted to. And then another topic called condition variables, but we could talk about that in a later class. What I just wanted to go over was the idea of creating multi-threaded programming is pretty simple. All you're doing is saying, you decide how many threads you'd like to create. It doesn't have to be 2, as many as you want. You could make 10 threads, kick them all off, and now your process is 10 children threads that are all sharing the operating system. It's time. But then the thing is, you have to watch out if these threads start sharing any resource, the printer, the files you're opening and closing. You want to make sure they're not corrupting the data. So you want to use these semaphores to block the threads or intentionally stall the threads so that your data ends up not being corrupted. So the idea that we're introducing threads is a good idea. We can get stuff done much faster, but now we've introduced some error proneness that we have to watch out for. And if you think about it, there's just many combinations where things can go wrong. So we want to develop like certain programming practices to make sure that stuff doesn't happen. Okay, so any question? Like I say, this is kind of a theoretical talk. Next class we'll code it up. So instead of it being a P function, which is just the guy who invented it, this will end up being, depending on what operating system we're looking at, but this could be, what would you, by the way, what would you name these functions? Obviously P and V you're not going to hold up. But if you, based on what you think they're doing, what would you call these things?
Start and stop.
Stall and
Lost and unlocked.
Wait, stall and what?
Free or free up or something?
Yeah, you know what ends up being, I think it was a tough thing to name because you're calling it stall, but it may or may not stall,
Yeah.
right? Because if the thing's available, you won't stall. And if it is not available, then you will stall. So something like
Take and give.
get or stall, might have been, yeah, maybe
Shut
get
them out the clutch.
or stall. And then this would be return.
Give and take.
Well, so what this thing basically says, if anyone is stalled, unstall, unstall and return?
Neutral.
I mean, I don't, there was really no great name for this, right? But if you wanted to, you know, be a longer name, it would be something like get or stall, and unstall or free up. Unstall or free up might have been a good name for this one. But anyway, it ends up being, the two most popular sets of names for these ends up being lock and unlock, and wait, which is like you're saying, stall, wait, and signal. Those are the two most popular combination of names for these two functions. So lock and unlock. So lock implies you're getting it and you're locking the guy behind you, but you might get stalled. So lock is a little confusing of a name. And unlock means you're letting it become a free-for-all, but you might be just moving someone off the waiting queue back to ready, and it means it's still locked. So none of these names are perfect, but yeah, the name unlock, after the unlock routine runs, it still might be locked if there was someone waiting and you just moved them back, it's still locked. So there's no perfect name for this, but like I say, the two most common sets of names that a programming language uses is lock and unlock, and wait and signal. But when you read if you read literature about it, sometimes you'll see this P and V thing. So I just want to tell you where that came from. But that's they all have this, whichever way you see it, if you see a P function, a lock, or a wait, it always means the same thing. Check if the resource is available, if not, go to the wait queue. And the P one, whether it's called, I'm sorry, the V one, whether it's V or unlock or signal, it always means the body of it is the same. It basically says, I'm done with this resource. Is someone waiting? I'll move them back to ready. If not, I'll make it free. Okay.